So what are all the things which we have discussed in the last class? Students, anyone, can you explain? What are all the things which we have discussed in the last class? Students, anyone? Anyone here? Around 60 students were there. I'm asking to you only. Am I audible?
Yes,
Yeah.
we discussed about basic convection concepts and like boundary layer concepts and the formulas associated with
Okay.
it, and
What is velocity
for
boundary layer? What is thermal boundary layer?
velocity boundary layer is like the region just above the solid material where the velocity of the fluid is 0 point up to 0.99% of
The free stream velocity
velocity,
of the
free
fluid.
stream
Yeah,
velocity.
that's very good. What about thermal boundary layer? What about thermal boundary layer? It's almost similar, right? So the temperature varies from 0.1 percentage of 0.1 percentage of the temperature of the surrounding fluid to 0.99 percentage of T infinity, right? So so that is a to be thermal boundary layer, and usually what happens is Prandtl number, right? Another dimensionless number has some effect on the thermal boundary layer. And similarly, we have two things. One is local heat transfer coefficient, the other one is average heat transfer coefficient. We will be always taking into account of the average convection heat transfer coefficient. Okay, the local heat transfer coefficient depends upon your particular point, okay, local point, whereas over the entire surface or up to a particular point, okay, from the leading edge, okay, we will always consider the average convection heat transfer coefficient, not the local convection heat transfer coefficient. And similarly, we also discussed about Reynolds number. What is the significance of Reynolds number, especially in case of forced convection? Anyone? What is the significance?
It tells whether the flow is turbulent or laminar.
Yeah, it gives us an idea about whether the flow is laminar or turbulent. And here also you can see here the examples for force convection, airflow, wings, buildings, a bank of heat exchanges, etc. were taken, especially external flow. Okay, when we are talking about external flow, we are not talking about internal flow. Okay, so these were taken as examples of force convection. And I have already told you, right? Usually there will be temperature difference, and usually what happens is in case of force convection, bulk motion of the fluid particles will be there, right? That is very very important, that word bulk motion of the fluid particles. It is due to the random motion of molecules diffusion and the bulk motion of the fluid particles. Okay. So that is also very very important. Okay. And in case of natural convection, okay, due to the density variations of the fluid, usually what happens is heat transfer takes place. And I have already told you about the examples, two examples, one chill water and one hot water in a tumbler, right? And after some time, what happens is the temperature remains the same. What happens there? Which law of thermodynamics is applied to it? Can anyone can say it? Which law of thermodynamics? One tumbler you will be having hot water, and the other one you will be having chill water. And what happens to it after some time? When
Second process direction is given. Like
yes, very good. See, in case of hot water, what happens is the temperature is at, see, zeroth law of thermodynamics. When two bodies are in thermal equilibrium with a third body, then the two bodies are in thermal equilibrium with each other. So what happens is the chill water will be at a lesser temperature, and when it is placed in atmospheric air, slowly after sometimes the atmospheric air, the heat energy from the atmospheric air will be taken, so that heat is transferred from the air to the water, so that the water attains the atmospheric temperature. And similarly, in case of hot water, the heat is transferred from the hot water to the atmospheric air. So in this case, the heat transfer takes place from the hot water to the air, whereas in this cold water case, the heat is transferred from the atmospheric air to the chilled water. So that what happens is after some time, after say 1 hour or 45 minutes, both the fluids will be at the same temperature and it will be in thermal equilibrium with the third body, which is nothing but the air, surrounding atmospheric air. Okay, so for zeroth law of thermodynamics can be explained very easily with this concept. Okay, so only thing is you should have either heat transferred from the hot body to the fluid, or sometimes you will be having heat transfer from the hot fluid to the cold body. I think I have explained both the cases very well with this particular zeroth law of thermodynamics. All of you are able to understand this. Either the heat transfer will be from the hot body to the cold fluid, or from the hot fluid to the cold body. Is it fine? Is it fine,
Yes, sir.
students? Okay. So, and we have discussed about the Reynolds number, the critical Reynolds number. We know that it is again. We also discussed about the local friction coefficient as well as average friction coefficient. Generally, we will be considering the average friction coefficient. That is local friction coefficient is given by shear stress divided by kinetic energy of the fluid of rho u infinity squared, where rho is nothing but density and u infinity is nothing but the velocity, tau s is nothing but the wall shear stress. Okay, and then the drag force is also calculated by tau s into as. Okay, so with this formula we can easily calculate it, and usually mu is taken as the density, sorry, not the density, dynamic viscosity of the fluid, and du by dy is the velocity gradient perpendicular to the wall. Okay, and I have already told you about, yeah, of course, we have discussed about the velocity boundary layer concept and thermal boundary layer concept. Okay, and we also discussed about the Reynolds number. Okay, for internal flow it is 2300 and external flow it is 5 into 10 power 5. So external flow or flat plate only. Okay, don't apply this for cylinders and spheres. For cylinders and spheres it will be different. Okay, so critical Reynolds number is 5 into 10 power 5. And so the first thing you have to find is you have to find out ud divided by nu or ul divided by nu, whatever it is. Okay, when it is sphere or cylinder, d will be diameter will be considered, for flat plate the length is considered. Okay, and actually due to the time restrictions I will not be going through uh, all the problems, but there are some problems. For example, uh, in some problems along the length side the wind will be flowing or the fluid will be flowing, sometimes along the width side the fluid will be flowing. Okay, so in that type you will be asked to find out what is the heat transferred. Okay, so the direction also changes. Okay, in some problems I think in Rajput there are one or two problems like that. Okay, which will be quite interesting. Okay, if the flow direction is changed, okay, what happens to the heat transfer of a flat plate? Okay, so that type of problem is also very, very important, but I don't know whether time permits or not. But try to go through the solved examples. There are in Rashford, there are so many examples which were solved. Okay, so you should know about laminar flow and turbulent flow. We already you might have discussed, right? Ordered fluid motion with identifier streamlines on which fluid particles moves, or particles move in a very streamlined manner, that is said to be laminar flow, whereas in case of turbulent flows the zigzag motion of the fluid particles will be there, irregular fluid motion with velocity fluctuations will be there, and a larger delta thermodynamic boundary layer thickness with flatter velocity, temperature, and concentration profiles is also there in case of turbulent motion. And similarly, uh, we have this laminar region, transition region, and turbulent region. Okay, so it will be there, right? And um, yeah, the effect of Prandtl number. Already, I have already told you in the last class itself. The Reynolds number is nothing but the ratio of inertia force to viscous force, whereas in case of Prandtl number, it is momentum diffusivity to thermal diffusivity. Okay. Now, what happens here is you can see, yeah, these are all some, yeah. if the Prandtl number is very much greater than 1, usually for oils it will be very much greater than 1, and then viscosity value is very much greater than the diffusivity, thermal diffusivity alpha. Okay, whereas in case of airs and gases, it will be almost viscosity is equal to the thermal diffusivity, or Prandtl number will be equal to 1. And in case of liquid metals, Prandtl number is very much lesser than 1, and the viscosity is very much lesser than the thermal diffusivity. So that's why I told you in the last class itself, in nuclear reactors we will be using the liquid metals. Okay, so that what happens is you will be having more heat transferred, or the diffusiveness is very much higher. Thermal diffusivity is very much higher. So thermal diffusivity alpha, what I have already told you in the very first class, right, during the expression itself. What it gives actually, what it indicates or what it gives, the alpha value. It defines. It defines the, yes. What it gives, ma? Thermal diffusivity value. Anyone? All of you are there or not? Ratan, Ankur, Charles, Ramkrishan.
To conduct the heat and like the ability of it to store it, so like
Yeah,
store
it
the.
gives us an idea about the degree of hotness or degree of coldness, or how fastly the body gets heated up, or how fastly the heat is given by the body. Right? That is usually given by the thermal diffusivity alpha. Right? So, and similarly, when we talk about the solution for especially how to get this thermodynamic boundary layer thickness, velocity boundary layer thickness, etc. Actually, as I mentioned earlier in the last class, we have to study about conservation of mass, conservation of momentum, conservation of energy. Okay, so all these three equations were involved. Okay, in fact, 8 equations were used. Okay, so the equations for two-dimensional laminar steady flow boundary layer concept is of mass, we will be using this dou u by dou x plus dou v by dou y, which is equal to 0. For momentum, u into dou u by dou x plus v into dou u by dou y, which is equal to u infinity du infinity by dx plus dou by dou y, v into dou u by dou y. Similarly, for energy, conservation of energy, we will be using this. Okay, and what happens here is, after from these equations, okay, Blasius has given the exact solution. Okay, or this boundary layer thickness, okay, the velocity boundary layer thickness del by x. Okay, del is nothing but thickness and x is nothing but the length from the leading edge. Okay, I have already told you what is leading edge and what is trailing edge. What is leading edge here? What is leading edge? What is leading edge and trailing edge?
The edge that first comes into contact with the fluid is called
Yeah,
leading edge.
the leading edge is the one which faces the fluid, or the fluid particles comes in contact with the leading edge first. Okay, the trailing edge is the edge which is further away from the fluid stream. Okay, so now del, which is equal to 4.99 into x, or 5 into x into Reynolds number per whole power minus zero point 0.5. Okay, so um, that formula is there in the data book. I had to showed you yesterday itself. I showed you yesterday. What is the page number? So you can see here in page number 111, you will be having the different things. Okay, what is Bayer number, Euler number, Fourier number, Freund number, Grashof number, Graetz number, Rayleigh number, Prandtl number, etc. Right, and you can see here the Prandtl number is Cp mu divided by K. Okay, molecular diffusivity of momentum by molecular diffusivity of heat. Okay, so and Reynolds number is inertia force by viscous force, UL divided by nu. And you can see here, is it visible to you all, students? Is
Yes,
it
sir.
visible? So 5x into Reynolds number per um, minus 0.5. Okay, so this formula is nothing but this is what given here. Okay, so del by x, which is equal to 4.99. The 4.99 they have approximated it to 5. Okay, and the x value comes to the other side. The x value comes to the other side, and the square root of Reynolds number per up to x is taken to the numerator, and it is mentioned as Reynolds number per up to the distance x whole power minus 0.5, and thermodynamic boundary layer thickness is this value into Prandtl number per minus 0.33, or del hx divided by Prandtl number per 1 by 3. Okay, so like this, you can find out. And similarly, I have already told you the average friction coefficient is the one which you are expected to find out. Okay, CFL bar, which is equal to 1.328 Reynolds number over the entire length. Okay, and similarly, Nusselt number also you have to find out the um, Nusselt number. Yeah, where it is. So for constant wall temperature problem, the local Nusselt number is 0.332, Reynolds number per zero point 0.5, Prandtl number per zero point 0.33. Okay, and that particular thing you have to use. Okay, so that is local Nusselt number. Average Nusselt number is 2 times of that. Okay, I think it will be given here somewhere. So if it is laminar flow or turbulent flow, or laminar turbulent combined, then you will be using these expressions 1.5.1 and 1.5.2. Okay, whether it is constant wall temperature, or whether it is when you consider laminar turbulent flow combined. Okay, or if it is constant heat flux, you will be using it. So these are all some of the expressions which you will be using. Okay, so you will be using 1.1, and you will be using 1.0, 1.1, and similarly you will be using this 1.5.1 and 1.5.2. So these are some of the expressions by which you can find out the average Nusselt number. Okay, average Nusselt number is nothing but 2 times of the local Nusselt number. That also you should know. I think usually it will be given here. I don't know. So in the textbook, you may see that average Nusselt number is 2 times. So what happens is instead of 0.332, it will be 0.664. Okay. So like that, you are expected to find these things. Okay. So in this particular page number, you are expected to uh, yeah, you can see here local Nusselt number is 0.339, Reynolds number per half, Prandtl number per 1 by 3. So all these solutions were given by Blasius. Okay. Similarly, skin friction coefficient also he has given tau W divided by half rho U infinity squared, which is equal to 0.664 divided by square root of Reynolds number up to the distance x. Okay, and similarly Reynolds number is ux divided by nu, or ul divided by nu, or ud divided by nu, depending upon the solid. Okay, whether it is a flat plate, then length is considered. When it is cylinder or sphere, diameter is considered. And similarly tau w is given by mu into dou u by dou y at y equal to 0, where mu is nothing but the viscosity. And average drag coefficient, local Nusselt number, and average Nusselt number. Okay, so you can see here the average Nusselt number is 2 times of the local Nusselt number. Okay, and similarly average convection heat transfer coefficient is calculated, h bar is calculated by uh, considering nu bar k divided by L. Okay, so this is the expression which is used to find out. And similarly, there is one more thing, the film temperature. The film temperature is often considered. Okay, you will whenever you want to take properties from the data book, you should not be taking it at the wall temperature or the solid surface temperature, or you should not be taking it at the fluid temperature. Air at 20 degrees C will be given in the question. So if air at 20 degrees is given, you should not take uh, 20 degrees C values. You should take solid surface temperature plus air temperature divided by 2. That is said to be the film temperature. At film temperature only, you should take the values. All of you understood this, students? Why film temperature is very, very important? Is it fine?
Yes, sir.
Okay. And similarly, when we talk about yeah, there are and these are all some other expressions which were there in the uh, in the data book. Okay, and Reynolds number, we know that up to UL by up to this 5 into 10 power 5 value. Okay, the flow is said to be laminar. Okay, beyond that it is turbulent. For laminar turbulent combined, I have already told you. For laminar turbulent combined flow, okay, you will be using this expressions. Okay, to find out the average friction coefficient up to the length. Okay, CFL. And for laminar turbulent constant wall temperature, the Nusselt number, average Nusselt number is calculated with this expression. Okay, Prandtl number per 0.33. And this expression is usually used for finding out the average Nusselt number, or generally you can use this expression also. Okay, either this expression or this expression can be easily used. Okay, depending upon the um, Reynolds number range. Okay, so depending upon the Reynolds number range, you can either use the first expression or you can use the second expression to get the solution. Okay, so that's what given here. Reynolds number greater than zero point 0.5 into 10 power 5. What is the friction coefficient and what is the average Nusselt number? Okay, so you can see these expressions. These expressions were here. Okay, average Nusselt number and CFL, average friction coefficient. Okay, so those things were there in the data book. Okay, so that's why without data book, if you come to the examination, it will be very difficult. You will not be able to memorize that. Okay, and similarly, when we talk about boundary layer thickness, okay, the boundary layer thickness increases from leading edge towards the trailing edge. Okay, you can see here from the leading edge to trailing edge, there is increase in the boundary layer thickness, and initial growth is fast. Okay, you can see here the initial growth is fast, from 0 to 0.5, whereas from 0.5 to 1, okay, the growth is lesser. Okay, and again it depends upon the type of flow, whether it is laminar or laminar turbulent combined, etc. Okay, depending upon the type of flow, you can see here initial growth is fast. Okay, growth rate and d del by dx proportional to 1 by square root of x. Okay, square root of x, x is nothing but the distance from the leading edge to the trailing edge. Okay, and similarly shear stress. Okay, the shear stress will be much more higher initially, and slowly it reduces. You can see here the wall shear stress. Okay, it is very much higher. Okay, at the beginning you will be having a higher shear stress. Okay, and slowly it reduces as the boundary layer grows. The wall shear stress decreases as the velocity gradient at the wall becomes less steeper. Okay, so this is what, so I have already told you about the aerofoil shape. Okay, aerofoil shape, everything, especially during the design of aeroplanes. Okay, so this is also very very important at the, especially at the contact point. That's why at the often you people you have seen that. Okay, usually that is the front end of the aeroplanes will be of the aerofoil shape, so that what happens is it makes, right, so that air will be moving towards the bottom and towards the top, okay, easily. Okay, it is not flatter, and I have already told you about the examples of ordinary cars and the wagon or the buses, which is more or less rectangular in shape. Okay, the problem is the wind resistances will be higher. Okay, in case of rectangular objects, rectangular shaped objects. Is it correct? All of you are able to understand this? Yesterday itself, I told you the wall
Yes, sir.
shear stress will be much more higher, right? So these factors are considered very very important when you consider the design, aircraft design or a vehicle design also. Okay, so that's why cars run faster and the wind resistance is lesser. See, what happens is all the automobile engineers, they say that around 30% of the energy is consumed by the wind resistance, 20 to 30%, depending upon the speed which you propel forward. That's also very very important. Okay, so the when you faster the speed, then what happens is naturally the wind resistance will be much more higher. Okay, so that's also very very important. And similarly, this is some of the difference between velocity boundary layer and thermal boundary layer. Velocity varies from 0 to 0.99 terms of u infinity, whereas in case of thermal boundary layer, the difference between t minus ts, it varies from 0 to 0.99. Okay, so the in case of velocity boundary layers, larger velocity gradients will be there, whereas in case of thermal boundary layer, larger temperature gradients will be there. Momentum exchange occurs via viscosity induced shear stress. Okay, viscosity induced shear stress. This is very very important. That's why the viscosity of the fluid is always very very important. Okay, and whereas here, what happens is heat transfer occurs via conduction plus advection, which is nothing but convection. Okay, and tau which is equal to mu into dou u by dou y at y equal to 0, which is equal to 0.5 into cf into rho u infinity squared. Okay, so the wall shear stress, okay, tau is nothing but the shear stress. It is found out especially when it comes to velocity boundary layer concept, whereas in case of thermal boundary layer concept, the heat flux is very very important, and we will be able to find out the heat flux in case of thermal boundary layer, q equal to ha del t or q equal to h del t. In case of, then we will be able to find out the heat flux. Okay, so wall shear stress is see, that's why depending upon the applications. Okay, in case of as I mentioned earlier, aircrafts and all, we will be talking about the wall shear, right? Whereas here when we talk about for example internal combustion engines and all, the how much rate of heat transfer to the upcoming stream of air or to the surrounding fluid is very very important. Okay, so for different applications we will be using different things. Okay, and the key challenge is to find out the friction coefficient. Here the key challenge is to find out the convective heat transfer coefficient, and the boundary layer thickness is related to nu viscosity, whereas boundary layer thickness, thermal boundary layer thickness is related to diffusivity. So these two things I already told you, right? Viscosity is the one which decides the boundary layer thickness in case of velocity boundary layer, whereas in case of thermal boundary layer, the thermal diffusivity is the one which decides. Okay, so these are all some of the numbers, and you can see here the effect of Prandtl number. I already told you, liquid metals, the liquid metals values will be lesser and oil values will be higher. Okay, and you can see here water and gases. Okay, for gases it will be approximately 1, and water is also it will be around 10 power 0 to 10 power 1. Okay, so what happens is liquid metals having higher um, alpha value. So you can see here nu by alpha. So larger the alpha value, lesser will be the Prandtl number. PR, which is equal to nu by alpha, larger the alpha. So liquid metals will be having more thermal diffusivity. So it is used in reactors, whereas oils will be having higher viscosity. So it is used in as especially for lubrication purpose. It will stick to the solid, right? It will not easily move, right? We have lube oil. Yes, somebody try to ask something. Anything you want to ask, students?
No, sir.
Yeah. So liquid metals will be having higher alpha value. Oil will be having higher nu value. Okay. So thermal diffusivity is more in case of what's that liquid metals. What's that? Uh, Viscosity is much more higher. Viscosity is much more higher in case of oils. So the oils stick to the surface, it won't move easily. So it is, that's why oils were used for lubricating lubrication purpose. Okay, so del by del t, which is equal to Prandtl number per n. This is the relation which is given, which is used to relate hydrodynamic boundary layer thickness with thermal boundary layer thickness, or velocity boundary layer thickness with thermal boundary layer thickness. Okay, and similarly there are also other numbers, especially in mass transfer we will be considering Lewis number, which we don't want to discuss now. Okay, yeah, okay ma, the time is 8:40 now. uh shall I start the problem, solving the problem? Okay, let me start it so that students, all of you are there.
Yes, sir.
Okay, let me solve this in the evening again. We will solve it. Okay, so evening, all I expect all of you to join by 6:30. Okay, all of you. I don't want anyone to miss out. Okay, so because I know that on Thursday some of them You will be traveling to the campus. Okay, but Thursday class will be there. Okay, is it visible to you, students? Is it visible?
Yes, sir.
Okay, so what it has given is a plate of length 750 mm and width 250 mm has been placed longitudinally along the lengthwise in a stream of crude oil which flows with a velocity of 5 meters per second. If the oil has got specific gravity of 0.8 and viscosity of 1 stoke, calculate the boundary layer thickness at the middle of the plate, shear stress at the middle of the plate, friction drag on one side of the plate up to the middle of the plate. Okay, so these things were given. Now you are expected to write the given data. Students, am I audible?
Yes, sir.
So now it is given in the problem that a plate of length 750 mm and width 250 mm. Okay, it is mentioned here, and kinematic viscosity is given as 1 stoke. Okay, now we know that you should know that 1 stoke, which is equal to 1 stoke, which is equal to, all of you please note that. Please take a note. 1 stoke, which is equal to 1 into 10 power minus 4 meter squared per second. Okay, and it is also mentioned specific gravity. So specific gravity is mentioned as 0.8. Am I correct? Specific gravity is mentioned as 0.8. From that you can find out the density. Density is density of oil. Density of oil divided by density of standard substance. So what is the standard substance, ma? Anyone?
Water.
Water. So which is equal to specific gravity. Okay. Now, so density rho of oil is equal to specific gravity into density of water. So density of water, we know that it is 1000 kg per meter cube. Okay, so 0.8 into 1000. So it is 800 kg per meter cube. Okay, and we know that 1 stoke, which is equal to 1 into 10 power minus 4 meter squared per second. Now what we have is we have this all of you have taken down that,
Yes,
students.
sir. Yes, sir.
Now we have the flat plate. Okay, and the oil is flowing over it. So up to the middle of the plate, 750 mm length and 250 mm width. Okay, velocity is given as 5 meters per second. Okay, 750, sorry, 750, and what is this width? The 350, yeah,
250, sir.
250. Okay, up to the middle. So from the leading edge, so this is the leading edge. Okay, and this will be the trailing edge. Trailing edge. Okay, so up to the middle, so up to 375 mm. Okay, L equal to 750 mm up to the middle. So x equal to L by 2 given in the question. So 375 mm. Please substitute it in meters. 0.375 meters. Okay. Now we know that what are all things which were asked? Del Hx is asked, right?
Yes.
Hydrodynamic bond. So calculate the boundary layer thickness up to the middle of the plate. So let us calculate both thermal boundary layer thickness as well as velocity boundary layer thickness. Okay. So del Hx, which is equal to 5x into Reynolds number per minus 0.5. Del Hx, velocity boundary layer thickness, 5 into x into Reynolds number per minus 0.5. Okay, now we know that Reynolds number equal to ux divided by nu. Okay, so ux divided by nu. So we know that what is the viscosity? Viscosity is mentioned as 1 stoke, right? That is 1 into 10 power minus 4 meter per second. Substitute here. So what is the velocity mentioned here in the problem?
5 meter per second.
5 meters per second. Okay, so 5 into up to middle Reynolds number up to distance x 0.375 divided by 1 into 10 power minus 4. How much it is?
18,750.
So, and again here, it is nothing but 1.875 into 10 power 4. Am I correct, students?
Yes, sir.
Which is less than 5 into 10 power 5. Yeah.
Yes, sir.
What is the laminar turbulent critical Reynolds number?
5 into 10
5
power
into
5.
10 power 5. Okay. So, which is less than 5 into 10 power 5. So, the flow is always laminar. Okay. Suppose if you are asked to find out what is the what are all the other things also, you can easily find it out. Okay. So, 1.75. Now, find out del Hx. So, 5 into x value 0.375 into 1.874. Oh, sorry. Yeah, 1 into 10 power 4 whole power minus zero point 0.5. I have got this expression from here, ma. All of you are able to understand? See, it is nothing but 5 into x into Reynolds number power minus zero point 0.5. I have written that x value is this one and Reynolds number value is this one. So what is the del Hx value?
0.01369
0.01369
meter.
meters. So that is how much mm?
13.69 mm.
13.69 mm. Okay, so this is hydrodynamic boundary layer thickness. All of you have taken this, students? All of you
Yes.
have taken this,
Yes, sir.
everyone?
Yes, sir.
Okay, the next one is thermal boundary layer thickness. So use the relation. So for thermal boundary layer thickness, again, it is mentioned here, del
But
Tx.
we don't have thermal
Yeah.
diffusivity.
So Prandtl number is asked, right? So we don't know the Prandtl number, right?
So thermal diffusivity and other terms are not given, sir.
Okay,
Unfortunately.
okay, then no issues. Okay, so we can stop with the hydrodynamic boundary layer thickness itself. Okay, what is the second one asked? Shear stress, huh?
Yes, sir. Yes.
So, okay, boundary layer thickness, since the thermal diffusivity is not given, we will not be able to find out. Shear stress. Shear stress, what is the formula which is used to calculate the shear stress? The shear stress is calculated with the help of the friction coefficient, right? Shear stress is calculated. You can see here CFX local friction coefficient into which is equal to tau Wx divided by rho u infinity squared by 2. So CFX Cfx, which is equal to, so I am taking the formula from the data book only. Wall shear stress. Wall shear stress divided by half into rho u infinity squared. Tau w divided by 1 by 2 rho u infinity squared. Okay, so now we have to find out Cfx to find out the average shear stress. Okay, average shear stress or local shear stress, it's asked.
Local only, sir. Middle of the
Local
plate.
only, yeah, middle of the plate. Okay, so tau w will be equal to, tau w will be equal to Cfx into half rho u infinity squared. So we know that density, we know that velocity, but we don't know Cfx. Okay, so to get that Cfx, we should use this. Cfx is equal to 0.664 into Reynolds number per minus 0.5. So that formula we have to use. Cfx, which is equal to 0.664 into Reynolds number per up to x whole per 0.5. What it
Minus
is?
0.5.
Minus 0.5. Yeah, that's fine. Now substitute this value. How much we got? Reynolds number 1.
1.875 into 10 to the power of 4.
10 power 4 whole power minus 0.5. So what is this value, ma? Cfx
0.004849.
0 point
004849.
0.4849. So now that we can find out what is wall shear, local shear stress, Cfx into half into rho into u infinity squared. So please calculate it faster. 0.004849 into half into density. Density we have found it there, right? Around 800,
800.
right? Yeah, 800 kg per meter cube. So 800 into what is the velocity? 5 meters per second, right?
Yes, sir.
So what is the value, ma? Do it faster. You have another
48.49 Newton per meter square.
48.49 Newton per meter squared. Is it
Yes,
meter squared?
yes,
Correct,
sir.
no?
All says yes, sir.
Okay. Density is kg per meter cube, and this one is in u infinity is in meter squared per second squared. Okay. Now, what is the third one, which is asthma? What is the last one?
Drag force, friction
Drag
force.
force. Okay, drag force up to the middle of the plate. Okay. What is the formula to find out the drag force? Drag force formula is given in the question. It's not given. Okay. In the data book, it's given, ma? No, it's not given. So all of you please take down the drag force formula. CF drag force as you can take down CF bar into of rho u infinity squared into area of one plate, one side of the plate. Okay, so up to 50 percentage. Okay, up to 50 percentage of the sheet or the plate. Okay, we know that the area up to so we have to consider only 375 and 250. Okay, so it is in so you have to substitute in meters. So now CF bar is 2 times of average friction coefficient is 2 times of the local friction coefficient. Okay, so average friction coefficient will be 2 times of local friction coefficient. So you can you can multiply this value into 2 point not 4849, right? You can multiply it by 2 into point not 4849, okay, into a half into again row value is 800 u infinity. See here, yeah, 5 whole squared into uh, area of one side of the plate. One side is 0.375 into 0.250. 0.250. See, I'm substituting in meters, ma. This is in meters and this is also in meters. Okay, up to 50 percentage. Okay, so what is the answer? Drag force? It will be in newtons. Drag force will be in newtons.
9.0921 newtons.
9.09.
0921 Newton.
Okay, please check the values because in the textbook it is mentioned as other value. Okay, it comes around 11 or 12 like that. Okay, please check it out. Okay, ma. See, what is the question? It is up to the length, up to the middle, right?
Yes, sir.
Up to the middle. Okay, up to the middle. So yeah,
9.1.
10.1.
9.1 I'm getting.
Yeah, then it's fine. Up to the middle. Up to the middle means you have to substitute this value only. That is correct, ma. What you have found it is correct. Okay. So what I will do is,
Sir, we are late for next class, sir.
yeah. Yeah. All of you please take down both the questions which is given in the chat box, and we will meet again by 6:30 in the evening. Okay. Thank you. Thanks for attending.